Me.
Okay, cool. I hope I don't regret saying that, but I love logs. But not to say that I can't be outsmarted by some of the more difficult problems. But what do we got?
Yeah. Okay, so this one we're not expanding, like compressing the logs
Okay.
back into it.
Mm-hmm.
So 1/3, then a bracket, I think, yeah, bracket, and then 2 natural log x plus 3 plus natural log x minus natural log of x squared minus 1, close bracket.
Okay.
Yep, and we're just supposed to compress that
All right.
to a regular one.
Let's start by distributing the 1/3.
Okay.
Okay. So that gives us 2/3 natural log of x plus 3 plus 1/3 natural log of x minus 1/3 natural log of x squared minus 1.
Okay.
Okay. Now let's move the coefficient that's in front of natural log to an exponent.
Okay. Oh, okay. So move the 1/3 into an exponent.
Basically going in reverse.
Okay.
X plus 3 to the 2/3 plus natural log of x to the 1/3 minus natural log of x squared minus 1 to the 1/3. Still with me?
Yeah.
Now let's compress. In other words, let's make those two multiply and that third term divide.
Okay.
Okay? So that becomes natural log of, let's see, we have x plus 3 to the 2/3 times x to the 1/3 all divided by x squared minus 1 to the 1/3.
Okay. This one's the 1/3. Is that our final answer?
I don't know. I'm looking at it.
Huh.
I think maybe it is. Let me see if there's anything we can do to that. Do you have answers on these or not?
I think I do. I think I'll check. I think I took pictures. She makes like an answer key, and sometimes she like does it at the very end of class, and you can't take pictures. And sometimes she does at the beginning. Yeah, I actually do.
It's always nice to have answers so you can at least verify that your method works.
She didn't distribute out the 1/3 though. So she kept the 1/3 on the outside,
Oh,
and then she put the other exponents in front.
so what was her final answer?
Natural log of cube root x plus 3 squared x.
Cube root.
Okay, sorry. Cube root of x plus 3 squared. Oh, wait, you want the first?
Okay, that's the same answer. Keep going.
You want our final answer?
Well, so far what you've given me is that. In other words,
Yeah.
if I multiply those two exponents together, I get 2/3.
Mm-hmm.
Yeah, tell me what her final answer is.
Natural log of the cube root of x plus 3 squared times x over x squared minus 1.
So what happened?
Yeah.
So what happened to her 1/3?
But she has everything under a cube root, not just x plus 3.
Ah, that's what's going on. Okay. So she
So I didn't.
applied the cube root afterwards, kind of
Yeah.
like this. Oops, sorry. Let's see. It's x plus 3 squared times x all over x squared minus 1. All of that to the 1/3.
Yeah.
That's her final answer?
Yeah. She has. Yeah. Except instead of 1/3, she has a root 3. Like the 3 and then the root.
Square root, the radical
Square.
sign, yeah, which is the same
Yeah.
as 1/3.
Uh-huh.
Okay. So she has her answer looking like this. Natural log of the cube root of x plus 3 squared times x all over x squared minus 1.
Yep. Yeah, that's her answer.
Looks. All right, that's the same as this answer. In other
Okay.
words, when you take an expression to an exponent, a fractional exponent, you multiply the exponents. Why she didn't take it to the last step, I'm not sure. Because you can multiply that 1/3 times the 2 to get 2/3. You can multiply the 1/3 times the 1 of the x to get 1/3. And you can multiply it by that to get 1/3. So it seems to me like that should be the answer.
Yeah, that makes sense.
If you do everything you can do.
Mm-hmm.
Not sure why she left the 1/3 separated out. Let me see if I can figure out. I don't think so. I don't know what the downside of distributing this 1/3 is immediately, and then applying it as an exponent.
Okay.
I think it's the same answer. 95% sure that it's the same answer as what she gave.
Yeah, I mean, I think it is too, because you do 3
Yeah,
by 2 and the 1/3.
yeah. In other words, you can always distribute these coefficients of logs. When you have a coefficient, a number in front of the log, you can take it to the exponent. And that's all
Yeah.
I'm doing if I distribute that 1/3 first.
Okay.
All right, let's do another one.
Okay. The next one is solve the exponential equation algebraically and then approximate the results to 3 decimal places.
Okay.
So this one is 2 times 5 to the x power equals 32. And I mean, I don't know why I was stumbling on this one, but I couldn't get it in class.
And the x power does not apply to the 2. It's just applying to the 5.
Yeah.
In other words, there's no parentheses. So the first thing we can do is divide by 2.
Okay.
Now, that is not something we can solve algebraically. We can solve it using logarithms, but that's not algebraic solution. If I had 4 to the x equals 16, I can solve that algebraically. I know x is 2.
Yeah.
But if it's not an integer situation, in other words, the answer to this is not going to be an integer. So there is no way to solve it algebraically. I cannot convert 5 and 16 to the same common base. So the only way I can solve this is using logarithms. And it doesn't matter which log I want to use. I can take natural log of both sides. Okay. The key is once you've taken the natural log of the left side, then you can bring the x down in front. So it looks like this. Now you have a solution.
Okay.
Now you have to get that number out of your calculator. And then what did they say, rounded off to 3 decimal places?
Yeah.
Okay.
So that becomes natural log 16 divided, whoops, natural log of 16 divided by natural log of 5, and it is 1.722.
And that makes sense, because if we go back to our original problem, which was this, nat 5 to the x equals 16.
Mm-hmm.
Well, if 5 is 1, the answer would be 5, but if x is 2, the answer would be 25. So x clearly has to be between 1 and 2.
Okay.
Okay, so that answer makes a lot of sense. And incidentally, when I took the natural log of both sides, I could have actually used common log. I could have used log base 17. Here's the thing about logs that is a bit of an oddity. Natural log of A over natural log of B is equal to the common log of A over the common log of B, and it's equal to the log base anything you want of A
Okay.
over the log of base 17 of B. Okay,
Huh.
so all of these ratios are the same no matter what A and B are.
Okay.
So that being the case, it doesn't matter whether I do common log, natural log, anything, because I'm going to end up with a ratio of logs here. So it doesn't matter if that final ratio is common log of 16 divided by common log of 5, same 1.72. It said rounded off to 3 decimals, I thought.
1.722. I said that.
Oh, okay.
Yeah. That's okay.
I didn't hear the second 2. Okay. All right. Now, usually, I've had problems before where you get a problem like this.
Okay.
Okay.
Oh.
This you can solve without logs. I can solve this algebraically, and I do it by letting 4 equal 2 squared, and I'm going to let 8 equal 2 cubed. Now I'm going to use the law of exponents, making that 2 to the 2x, making this 2 to the 3x minus 9. And now because I have the same base, I can equate exponents. So I can say 2x equals 3x minus 9, making x equal 9.
Okay.
Okay? Notice I didn't use logs one time, but that was only because both of these numbers, 4 and 8, share a common exponential base. I don't mean a common factor. Their common factor would be 4, but I can't really write 8 as 4 to some power.
Okay.
So what I'm looking for when I'm trying to do this using an algebraic solution is a common base between those two numbers. What's a common base between 9 and 27?
9.
Nope, that's a factor.
Oh. A common base 3.
3. In other words, I can write 9 as 3 squared, and I can write 27 as 3 cubed. There's your common exponential base.
Okay.
Okay, it's not always obvious because most people want to think in terms of factoring. You know, you spent your whole life in math thinking of factoring. So you kind of have to switch your thinking into what is a common exponential base for these kind of problems. But even if you didn't have a common exponential base, I could solve this logarithmically. In other words, I could always say x natural log of 4 equals x minus 3 times the natural log of 8. And
Okay.
would eventually, you know, these are just numbers. Don't be confused when you see natural log or log of something. That's a number. That's all it is. So I've got an equation there with one variable. I could come up with a solution.
Okay.
But if it's the perfect type equation, sometimes you can solve it without logs, and has to have a common exponential base to do that.
All right. Okay. Okay. Next problem is we get to solve the logarithmic equation algebraically and then approximate the result to the nearest 3 decimals.
Okay.
And so this one is natural log of 4x equals 1.
Okay.
Oh, wait. Whoops. I'm looking at the wrong problem. I'm sorry. It's still natural log. It's natural log of, here, I'll wait for 1 second. Sorry. Sorry about that.
No problem.
Okay, natural log of square root x minus 8 equals 5.
Okay. The way you solve log equations, once you get it to a log of an argument, is make it look like an exponential equation. In other words, what's the exponential equivalent of that? This is really almost the most important part of logs, is being able to convert between logarithmic and exponential and vice versa.
Isn't it e to the 5th equals the square root of x minus 8?
Yep. And let's do it that way.
Okay.
Okay? Just exponents work better when you're dealing with either logs or calculus or anything else. And you quickly dispense with these radical signs. Now,
Okay.
that's a number, right?
Yeah.
Okay. But how would you initially solve this? What would your first step be here?
Trying to find a common base.
No. In other words, what we have here is an algebraic expression. First of all, it's algebraic because the variable is in the algebra line. It's not in the exponent.
Okay.
Variables in the exponent, that's when it's difficult. That's when you have to employ logarithms. But this is pretty easy. What if I square both sides for starters?
Okay.
Well, that gives me e to the 10th. When you square e to the 5th, you get e to the 10th. You square that side, you get that. So x equals e to the 10th plus 8.
Okay.
Okay. Now, let's go back and make sure that I can do it another way. Well, if I wrote that natural log of x minus 8 to the 1/2, then I could put the 1/2 over here, right?
Okay, yeah.
In other words, that's the same thing. Haven't changed anything. Now multiply both sides by 2. And now apply your formula. E to the 10th equals x minus 8.
Okay.
And then you can get the same answer.
Okay.
All right. That's probably the best. Well, I hate the fact that she says turn it into a decimal. I really do. That's just a terrible thing to ask. Because this is a precise answer. That's the most precise answer you're ever going to get.
Okay.
That's precise to 1,000 decimal places.
Okay.
If you have to turn it into something that has 3 decimal places, then you can certainly get that number out of your calculator, add 8 to it, and round it off to 3 decimal places.
Okay.
It's going to be over 1,000, I know that, because 2 to the 10th is 1,000. So e to the 10th is 2.7 to the 10th. That's probably more like 50,000.
22,034.
Okay, so 22,000. That's after adding 8 or not?
Yeah, after adding 8.
Is there any decimals after it?
22,034.465.
So that's our answer. Okay.
Yep.
Notice that's not as accurate as this.
Okay.
It just isn't. It's like saying,
Yeah.
well, pi is pi. Well, I can write pi to as many decimal places as you want. There's still no way that's ever going to be as accurate as that. So you
Okay.
don't do it. You leave it in pi. When you give an official math answer, you leave it in terms of pi.
Okay.
And same thing with e. E is no different than pi. E should be left as e.
Huh. All right.
If you're an engineer and you have to build a building and the length of something is this, then you have to turn it into a decimal. That's the only way you can do it. But if you're a pure mathematician, then that's the answer you always want.
Okay.
But
Okay.
obviously do what your teacher asks. So if she's
Well,
asking
yeah,
decimal point.
it's like what the book asks.
Yeah.
Okay. The next problem is 2 natural log of x equals 7.
Okay. Always when you're trying to solve natural log equations, you want to get it down to that. You know how when you're solving a normal equation, you want to get it down to x. But when you're solving logarithmic equations, you want to get it down to this. And to get it down to that, I needed to divide both sides by 2. So
Okay.
I end up getting this. Now, next step.
And you could loop it.
Convert it to an exponential expression.
Yeah.
Not sure what you mean by loop it.
Sorry. Looping is kind of like a method we were taught back in when I first had algebra. It's where you kind of like just draw an arrow and you start at the bottom of the x.
That's exactly what I do. In other words, what I do is I take that raised to the power of that equals that.
Yeah.
Which works great as long as the natural log is on the left. If I do this, which is the same exact expression, doesn't work so great. In other words, now I have to take e to the 7/2 equals x. So that's a fine method. It's one I use myself as long as the natural log is on the left side. So I can say e to the 7/2 equals x. That number you can get out of your calculator.
Yep. E to the 7. Sorry, I'm just catching up.
All right.
Equals x.
Now, the truly interesting log equations are where you have to compress it first. Do you have any of those? And they're interesting for one really important reason, and that's the domain considerations.
Yeah. Okay. I have one. I don't know if it's a compressed one or not.
Well, what I'm talking about is if I had something like this. Okay. First step would be to compress it. So it's x times x plus 1. Second step would be to expand that. So it's x squared plus x. Third step, e to the 5th equals x squared plus x. That's just a quadratic that you can solve.
Okay.
You're going to get a positive and a negative solution. And the negative solution you have to throw away because it would violate that domain. You cannot take any kind of log of any number that is not positive. You cannot even take the log of 0. In other words, the domain of natural log is more restrictive. If I say, what's the domain of that? Well, x has to be greater than or equal to 0. But if I say that, x has to be greater than 0.
Okay.
Okay? So always remember that. And a lot of times when you're solving log equations like this, where you have to compress it, turn it into a quadratic, solve the quadratic, you get a plus and a minus solution. The minus solution is not going to work because that would make that a negative.
Okay.
Okay? You probably have some of those. You just haven't gotten to them yet.
Okay. Yeah. Okay. The next problem is 5 log base 10, so just common log, x minus 2 equals 11.
Same solution. What's the next line?
Log x minus 2 to the 5th.
No, you're compressing it. We don't want to compress it.
Okay.
Let's just divide both sides by 5.
Divide by 5, yeah.
In other words, this is going to get us to the quickest exponential equation, and that's what we need. So what's the exponential equation that results from this?
Log base 10 x minus 2 equals 11/5.
Okay, and then convert that to an exponential equation. That's the logarithmic representation of that.
Okay.
What's the exponential?
10 to the 11th fifth equals x minus 2. So 10 to the 11th fifth plus 2 equals x.
Yep. And again, that's a number you can get out of your calculator. Just in your calculator, make it 10 raised to the 2.1 power, 11/5.
Okay. Equals 163.489.
Sounds right. And then add 2 if you haven't already.
Yeah, added 2.
Okay. These are all relatively the same in nature. I'm a little surprised.
Oh, here's a...
Every one of these, you start out by dividing by that coefficient.
Okay. Yeah, here's a compressed problem.
Okay.
56. It is, okay. Or it's expanding.
Okay.
So it's log base 2 square root of x multiplied by y all over, or y to the 4th, all over z to the 4th.
Okay. Always get rid of your radical signs as quickly as possible.
Okay.
That's one way to do it right there. Okay, I don't need the parentheses around the y.
Okay.
So now expand that.
Log 2, or would you have 1/2 log?
Well, let's do it one step at a time. Yeah, that's eventually what you're going to do. But to make it a little bit clearer, let's do it like this.
Plus log 2 y to the 4th minus log z to the, or log 2 z to the 4th.
And now you can bring these exponents and put them in front. So your final answer is this. And incidentally, these rules for logs only apply if they're the same base.
Okay.
In other words, if one of these was log base 2 and the other was log base 3, I cannot do anything with it. I cannot compress it, expand it, combine them. They're just different numbers.
Okay.
This is a compression, or this is definitely an expansion problem, but not quite what I was looking for. I was looking for a log equation that requires you to compress in order to solve.
I can see if I have any of those in the book.
Well, we can go on. We got a half an hour here. We can just go forward. I would imagine that, well, maybe you haven't gotten to that yet. That's the
Well, I have one more problem
Okay.
in my homework, and then I'm like free.
Okay.
The last one is natural log square root x squared times x plus 2.
Square root of x squared times x plus 2?
Yes.
So that?
Yeah. Uh-huh.
Okay.
That'll be the same.
Is that it?
Yeah.
Okay. Now, you usually want to go in the following order when you're expanding stuff, is to bring the exponent down first. Okay. So the first thing I'm going to do is that.
Okay.
Now I'm going to separate those two there. So I got natural log of x squared times 1/2 plus, and the 1/2 has to go with both terms, natural log of x plus 2. With me?
Yeah.
Now I can take that 1/2 and put it back with that exponent and turn that thing into natural log of x plus 1/2 natural log of x plus 2. And whether you choose that to put that 1/2 as an exponent or a radical sign, I don't know if there's a preference or not. Certainly you want to simplify that to natural log of x, but the only thing I could do with the term on the right is to put the 1/2 up here as an exponent, or I could put it as a radical sign. Either one is correct, as this is also correct.
Okay. Okay.
You might want to look at the key if you have a key on this one, just to see what the format of the book or your teacher.
I have. That was the same answer.
This is exactly?
Yep.
Okay. All right.
Well, that was the extent of my homework.
Okay, well, let me make one up, because if you haven't gotten to these yet, you will.
Okay.
Okay, how would I solve this log equation? Solution is always going to be this method where you compress it to a single log expression.
Okay. So could you combine the logs?
Okay, so how do you turn that on the left side into a single log expression?
Oh, doesn't that become log base 10 to the 1?
Well, I got to multiply these two numbers, so it's this, right? That's what the left side.
Okay.
Okay, and that is the log of x squared minus x. So we have that equaling 1.
Okay.
And let me think for 1 second here if I could have made this a little bit better. I could have. Let me make this a 3.
Okay.
Okay. Now that becomes 3x. With me?
Okay.
Now how do I
Yes.
solve this?
Now would you turn it into exponential form?
Yep.
So that'd become 10 to the 1, which is just 10, equals x squared minus 3x.
Correct. Now it's a quadratic, basically.
Mm-hmm.
Let's move the 10 to the other side.
Okay.
Now factor. And this is the way a lot of log equations unfold exactly like this. You end up with a quadratic. You're going to factor it into x minus 5, x plus 2,
Okay.
which makes your solutions x equal 5 or x equal minus 2. Okay?
Okay.
Now, if we go back to the original equation, we can see that the minus 2 violates the domain. That's
Okay.
not a solution. Only the 5 is the solution.
Okay.
Okay, and that's
Why does the minus 2 violate the domain?
because if we plug in x of minus 2, we're taking the log of a negative number.
Oh, okay.
Remember, it always has to be positive. You cannot
Positive.
even take the log of 0. If we'd have come out with a solution of 0, that would have violated the domain also.
Okay.
Okay? And notice one other extremely interesting thing. If you plug it into that, it does not violate the domain.
Okay. Because that just becomes,
Well, that's a minus 2. That's a minus 5. Minus times a minus is a plus. I'd be taking the log of 10.
okay.
Okay? That tells you a lot about logs. It tells you that that is not 100% identical to this. In other words, I violate the domain only when I go back to the original problem. I don't violate the domain when I go to the compressed problem.
Okay.
And that is possible, and that is one characteristic of logs, is that you have to be very careful when you're testing the domain. It can frequently, I mean, who knew mathematically that it could, we're told these two things are equal, right?
Okay.
That's what they teach you.
Yeah.
They teach you that line number 1 is exactly the same as line number 2. Well, it isn't exactly the same.
Okay.
In other words, had they given me this as a start, that second line, then both of those answers would have been valid.
Okay.
Notice that when I plug in 5, I get a positive times
Oh, I
a
get
positive.
it.
And when I plug in minus 2, I get a negative times a negative, which turns positive. So if
Okay.
I start with the second line, both of those answers are valid. They do not violate my domain. But you
Okay.
almost never start there. I've never seen a log equation that starts here. It always starts up here. In other words, the uncompressed form of it. Very important that you always go there to test your domain.
Okay.
And
Okay.
furthermore, logs almost always have one of the solutions violate the domain. So this isn't something that happens just every now and then.
So
It
you
happens
always will usually have like one solution?
almost always, because you usually, if you have two logs, it turns into one quadratic. And
Okay.
quadratics always produce two solutions, and one of those solutions is usually negative, and the negative solution won't always violate this domain, but it will a lot of times. In other words, if I had
But
a
most of
negative
the
x in
time.
front of that, now it doesn't violate it, but the 5 does.
Okay.
And
Okay.
it's okay to have log of negative x, incidentally. It just means x has to
Uh,
be a negative number.
oh, okay.
Okay?
All right. Well, that makes sense.
Yeah. You just cannot have the entire argument be less than a positive number. But you can certainly have negative numbers in your argument.
Okay. Okay. Huh. That makes sense.
Yeah, it's an interesting dilemma. In fact, my pre-calc book has one particular problem where they really investigate this domain thing,
Huh.
but
Okay.
I don't have it open to that at the moment. But so, what else besides? Was it all logs?
Yeah. All we learned about was logs today in class.
Okay, let me think if I can even think of some interesting log questions that you haven't covered. You know what? Let me open my book. I really kind of would like to show you this one problem. Let's see if I can find it quickly. Logs have terrific applications in calculus.
Okay.
You wouldn't be able to do a lot of calculus problems without logs.
Okay.
Interestingly enough, for example, not that we'll go through this because you haven't had calculus, but if you've had limits, right?
Yeah.
That problem right there. I
Um.
think the answer is.
Is that the natural log or?
No, just the limit of x to the x power.
Oh, limit of x to the x power and x has to be above 0.
Well, this is one of the interesting problems in that you have stuff called indeterminates. Okay?
Okay.
0 divided by 0 is indeterminate. That could be 0, it could be infinity, it could be 6.
Okay.
No way to determine what 0 over 0 is. Obviously, 0 over a number is 0, and a number over 0 is undefined. It's infinite.
Yeah.
Another indeterminate is infinity divided by infinity. Another indeterminate is infinity minus infinity.
Okay.
None of these, you can't tell what any of these are until you do further work on the function. Well, one last indeterminate, which I still have yet to answer why this is true, is 0 to the 0 power.
Huh.
Why is that indeterminate? We are taught from the get-go that any number to the 0 power is 1. If I said x to the 0 power, I could say that's equal to 1.
Okay.
It doesn't matter if x is minus 10 or 100 million or negative a billion. It's still 1.
Okay.
But what about when x is 0? Well, then you have this situation. In other words, you're looking at 0 to the 0 power when x approaches 0. Well, the way you solve this is you take the log of both sides. In other words,
Okay.
I say that that's equal to some value y, and now I can take the natural log of that and the natural log of that, and then I can bring that x in front over here, and now I have a way to advance the problem.
Okay.
It's the ability to take the exponent after you've put it into a logarithmic expression, being able to take that variable exponent and put it on the algebra line is huge.
Okay.
That's how you solve a lot of calculus problems. Second, I just almost have it. What I was looking for here. Maybe not. Yes, there we go.
Okay.
If we use method 1 and take Okay, their method 1 is the log of x squared equals the log of 10 to the 2. In other words, what they did was they rewrote 2 as this.
Okay.
Notice that's a true statement. In other words, whenever you have the log base b of b to some exponent, it's all equal to the exponent.
Yeah.
Okay. And now, from the one-to-one property, I can say that equals that, right? In other words, if you got the log of something equals the log of something else, then the first thing is equal to the second thing.
Okay, yeah.
And then if I solve that, x is equal to plus or minus 10.
Okay.
Okay. Second method. Let me do it over here on the left. We got the log of x squared equals 2, which means that x squared equals 10 squared, correct? Which means x squared equals 100, which means x equals plus or minus 10 again.
Yeah.
Third method.
Oh, third method.
Third method, log of x squared equals 2. So I bring the exponent down. 2 log of x equals 2. Divide both sides by 2. I get log of x equals 1. And I get 10 to the 1 power equals x. What happened to my minus 10?
Oh. Huh.
In other words, the third method only gave me a plus 10.
Okay. What? Yeah, I understand why, but
Guess which method is incorrect?
The third method?
Yes. The first two are correct. In other words, and yet we didn't do anything wrong on this method, right? We did everything exactly like you're supposed to.
Yeah.
But we didn't get the complete answer. We lost one of the solutions by doing it like this instead of doing it the previous way. Hold on. Let me see if I can figure out how to go back to that page. Yeah. In other words, when I did it this method on the left here is pretty straightforward.
Yeah.
In other words, all I'm doing is converting it to exponential. And I get my proper solution. This method on the right is a bit unconventional, but it's certainly true and valid. I can write the number 2 as log base 10 of 10 squared. And then using the one-to-one property, I can come up with the same plus or minus 10.
Mm-hmm.
Okay. So, and if you were not sure of which of these three methods, all of which appear to be valid, are true, well, graph it. Okay? If I graph it, I get a graph that looks like this. And then if I draw the line y equals 2, I can clearly see there's two solutions. One's at minus 10 and one's at plus 10.
Okay.
This line here is y equal 2. In other words, whenever you're trying to solve a problem by graphing it, well, I can graph the left side of the equation as y sub 1 and the right side of the equation as y sub 2. And in this case, y sub 2 is equal to 2. That's the right side of the equation. So I can always figure out the solution to this thing graphically by graphing natural log of x squared as one function and the next function y equal 2. And wherever they intersect is the solution. So graphically it tells us that plus or minus 10 has to be the solution.
Yeah.
Let me see what else it has to say here. Just 1 minute.
Huh.
Method 1 and 2 are correct. Method 3 fails because the domain of log of x squared is all real numbers, all non-zero real numbers, but the domain of log of x is only positive real numbers.
Huh.
Method
Okay.
3 violates an easily overlooked but important consideration, namely that the rule, you just, I won't read all of their explanation, but you have to be very, very careful about domains
Okay.
dealing with logs.
I don't think we've talked about in our class the domains with logs,
I
though.
don't think you have either because you didn't give me a problem that required it.
No.
In my book right now, I'm looking at 3 of them. So, and the fact, the school you go to, you're going to get it. You just haven't got it yet.
Okay.
Okay, you'll deal with logs and domains probably tomorrow or next day. In other words, you're just almost there.
Okay.
So I got a little bit ahead.
That's okay.
But yeah, it is good. It's better to get ahead than behind, right?
Yeah.
I mean,
That's
I'd
true.
rather stay ahead of it. It makes it a little more understandable when the teacher goes to talk about it in class.
Yeah. Definitely. Okay. Well, that's a lot more clarifying. Got to watch out for that other method, though.
I hope so. Yeah. Don't worry too much about those 3 methods. Worry more about violating the domain of your original function. In other words, the
Okay.
reason we could screw that up because we started out like that. If I'd have started out like this, that's not going to allow you to screw up.
Okay.
But, and you would say that this is equal to that, right?
Yeah.
I mean, log of x plus log of x is the log of x times x, which is x squared. The
Yeah.
problem is that there are no negative numbers that violate that. The domain of this function is all real numbers. Well, except 0, excuse me. All non-zero numbers. X still cannot be 0, but x can be
Okay.
negative and x can be positive because when you square it, it turns positive.
Yeah. And X can never be a 0 in a log.
Right, but if I look down here, the domain of x is positive numbers only. So if I'm starting there, I got to be very careful, and that's usually where you start. It's rare that an equation starts from there. It
Okay.
usually starts with a multiple log statements that you have to put together, and then you have to convert it, and then solve the quadratic, and then check your domain of the original function.
Okay.
Okay?
Huh. All right. So why can log never equal 0, though?
For this reason, all log expressions or all log discussions involve this. Logs are exponents, right? Right? That's what logs are. If you really want to remember one thing about logs, logs are exponents. Notice that my log here is x. These two
Okay.
expressions are the same, correct?
Yeah.
One is just the exponential expression, the other is the logarithmic expression.
Yeah.
Well, if I make y 0, how do you take a number to some power and get it equal to 0? You can't do it. There is no
Okay.
value for x that will produce a 0. Remember
Okay.
that if x is 0, the whole thing's equal to 1.
Okay. Yeah.
b to the 0
That's true.
is 1. Well, there is no value for x that'll make b to the x be equal to 0. Since y can never be 0, well, I can't let it be 0 here either.
Okay.
And it also cannot be negative. I cannot take a b to the x and produce a negative number, no matter what
Yeah.
x is, no matter what b is. Well, that's not quite true. This always presumes b is greater than 0. In other words,
Okay.
when you start your chapter on logs, this is the first thing they tell you. y equals b to the x, and b is a positive number.
Yeah.
And what that means is that y can never be 0, y can never be negative. And that's where the domain restriction comes from.
Okay. Oh. Well, yeah, okay, that makes sense.
Yeah, no, if I let b be a 2, well, what power would equal 0? It can't be. There's no value of x that makes that equal to 0, and there's no value of x that makes it equal to a negative number. So
Yeah.
b to the x has to be positive, then the domain on that has to be a positive number.
Okay. So is it possible to have an equation that's like got negative numbers in it, but it can't be solved?
When I say it can't be negative or 0, it actually can, but it invokes the complex number realm. In other words, it's like saying x can't be a negative number. Well, that's not quite true. I can take the square root of -7. It's root 7i.
Yeah, root 7i. Oh, okay. So
same those imaginary numbers, I applies to logarithms when you're taking the logs of negative numbers or 0.
Okay.
That's what produces imaginary numbers.
So when you start applying negatives, you start also using imaginary numbers like complex numbers?
Yeah, although you probably won't get into that.
Okay.
I've never actually seen a high school course get into complex numbers with logs. I know that it's true. They apply to logs just like they apply to square roots of negative numbers.
Okay.
But you won't touch on that, I don't think. And in terms of domain, the complex realm is not in your domain. When they ask about domain, they don't mean imaginary numbers. Otherwise, you know, the domain of that is positive x is greater than or equal to 0. Has to be. Okay, so when you're talking domain, you eliminate the complex numbers from consideration.
Okay. Okay. Well, that's a little more like understanding. That's how I put it. Yeah.
But that's why it can't be 0. Is because you cannot make y 0 from the original y equal b to the x.
Mm-hmm. Okay. Well, I mean, that's the extent of my homework and the problem, and time's almost up. Is there anything else you want to cover?
I don't think so. We've covered logs pretty good. The only part you hadn't covered yet is solving log equations, really. I mean, where you have to condense it first. And we did a couple of those, so you should be well prepared for that. And that's where your log is going to end, I believe. Unless your school gets into it a little deeper, which is possible. Your school always goes a little beyond the common core.
Yeah. I think we might do domains of logs and graphs of logs, and that might be it.
The graph of logs, pretty easy. If I want to graph the log function, starts at -infinity, goes through the point 1, 0, and then looks very flat after that.
Okay.
The key being that if you take the log of 1 or higher, it's a positive number. If you take the log of numbers between 0 and 1, it's negative numbers. In other words, if I take the log of 1/2, I know I'm going to get a negative number, right? 1/2 is right there, and I'm in negative territory. But if I take the log of 1.1, I'm in positive territory. I'm about there. Okay? And one other interesting thing about logs in the 2 minutes is this is the flattest function you will ever see. I have to go 2 miles in that direction to move up by 12 inches. In other words, this rises extremely slowly. I can make x be 100, and the log of x is only 2.
Okay.
If I make x be 1,000, the log of x is 3.
Okay.
Okay, so I have to really go a long ways in that direction to go up very much at all. However, the log of x as x goes to infinity is infinity. In other words, eventually, even though I'm only going up 12 inches for every 2 miles over, I'm still going to reach infinity on the vertical direction.
Yeah, because it's always continuous.
Yeah, exactly. It
Okay.
doesn't ever stop rising. It
Okay.
almost looks, if you looked at the log function, you would almost think that there's a horizontal asymptote the way it looks.
Yeah, that's what I was thinking.
But it's not. There isn't one.
Okay.
There's nothing that limits what the log of x can go to. You make x big enough, the log of x gets big, real big.
Okay.
All
That's fine.
right.
Okay.
Nick,
Well,
I will
that's
talk to you
a little more.
next time. I think you have a session Monday, I think?
Yeah, I think so.
Yeah, talk to you Monday.
Okay, thank you.
Bye.